conferencia de este ciclo emblemático que es Hablemos de Física. Y por supuesto, muchísimas gracias también, como siempre digo, a la Real Sociedad Española de Física, que colabora con la Facultad de Físicas en tantas cuestiones como esta, con la presencia de conferenciantes de enorme prestigio internacional. So it's my pleasure, Professor Yorke, to welcome you to University Complutense.
Thank you.
Yes. And thank you very much for taking part in this series of conferences aimed to inspire our young undergraduate students in many fields of physics. Yeah? And it's also a series of conferences that are also focusing in the possibility of bringing them closer to really leading physics figures, as it's the case of Professor Yorke, and also to talk about research challenging topics. So thank you very much. You have all the conditions for really a wonderful conference, a remarkable meeting, so please enjoy it. So, President.
Okay, so thank you very much. I just want to say that it is a pleasure having here Professor James Yorke from the University of Maryland. One of the good things of introducing really first-class scientists is that the introduction can be very short, because there is nothing more to be said, and it is known already of the speaker. And in this particular case, I will just say that he is full professor in Maryland of mathematics and physics, I think both. He was just telling me a moment ago that he became full professor of physics by via of mathematics, and that he has honorary degrees, and of course that he is one of the masters and fathers of the chaos theory. In particular, he wrote in 1975, if I am correct,
Yes.
a very famous paper with his collaborator, Tianyan Li, which gave name to the subject. It is the paper entitled Period 3 Implies Chaos. And having said that, I think that
If you want to know the theorem, you can
Yes.
look my name up in Wikipedia.
Oh, yes, of course. So, having said that, I think I'll move down and enjoy the talk of Professor Yorke. Thank you very much.
I'm delighted to be here. One of the aspects of chaos is that everybody knows about chaos. In fact, you may not know you know about chaos, but you live chaos. And when I named the field, I didn't know I was naming the field, but when I named the field, I was saying chaos that we see in mathematics is the chaos we see in our lives. And I will not be emphasizing the chaos in your lives, but I often like to begin lectures with some photographs I've taken. And in March, I took a photograph. I was in Spitsbergen, and this was the solar eclipse. This is a photograph just from the camera, no filter or anything. And we had a total eclipse. Another shot of the same thing is where the sun is just peeking around the moon. This was 1,200 kilometers from the North Pole. It was the only spot on Earth where you could actually see the eclipse. Often they are have a much longer span, but this one did not. Now, how is it that we can predict eclipses? We can talk about when eclipses existed in ancient China due to the records. So when you look at scientific models, some models have lots of noise built into them. It's pumped into the model. It's not generated by the model. But let's ignore those. Newton described how the solar system works in the 1880s. He was born 1842, and he described how the solar system works, and it remains one of the simplest examples, or clearest examples, of where it works with very high precision. Of course, he was not incorporating general relativity and so on, but that's a minor point. Without general relativity, we can still account for these eclipses and explain why they occurred, how much the Earth is slowing down. And what we have is a number of interacting cycles, and these are not chaotic. The fact that you can predict them means basically they aren't very chaotic. So you have the moon going around the Earth, and the Earth going around the sun, and the Earth moving in an ellipse as it goes around the sun. The moon is not really in an ellipse, but it's in an oscillating ellipse, which is changing in eccentricity. In order to talk about the Chinese, you have to figure that, well, right now, the North Pole points at the North Star, but that precesses every 20-some thousand years. You have to take that into account. So there are a bunch of cycles, all of which have to be computed if you really want to talk about the long history of these. So this, we would call such a motion, the motion of the Earth and the sun, for all practical purposes, it's quasi-periodic. That means it's got a number of different cycles. And when you have a model, you just pick a model at random. Don't tune the parameters for anything. You can see three kinds of motion. There are the periodic motions, very simple, a pendulum swinging back and forth is periodic. You've got the quasi-periodic ones. In fact, a detailed study of the solar system shows that Mercury is particularly got a chaotic element in its orbit, as does Pluto. But you've got three kinds of motions: the periodic, the chaotic, and the quasi-periodic. And those are basically the only things you see in these models. Now, a physicist friend of mine showed me this picture. This picture relates to an old story. And when I show this picture, some people know about this parable. This is the parable of the blind men and the elephant. So the blind men come across an elephant. But here you can see one of the blind men encounters the ear. And he says, the elephant is a fan, one of these big fans for cooling in ancient times. And another incorporates the tusk. And he says, the elephant is a spear. And another encounters the tail, and he says the elephant is a rope. This comes from a Buddhist parable 2,500 years old. And they are all encountering different aspects of this. Now, for the purpose of the Buddhist literature, what the Buddhist reader is being told is that there are many aspects of God, and if you only understand one aspect, you are like the blind men and the elephant. How many people have heard of this blind men and the elephant? So, many and many not. Good, now you've all heard of it. But from my purpose, chaos is like the elephant. There are many ways to encounter chaos. And so here we have these three kinds of behaviors. And here is a mathematical model. We say x goes to 2x mod 1. So that means that you think of a circle, and we're talking about an angle. And we measure the angle from 0 around to 1. Not to 360, not to 2 pi, just 0 to 1, revolutions. And we're only interested in the angle. So if you go around 5.5 times, we only count the half. That's what the mod 1 means. Throw away the integer part. And so it's a simple dynamical system. And we can try it. So you start off with a number like a third. Well, let's see. If this is angle 0, 1/3 of the way around is about here. And we double it. We get 0.66. We double it again, 1.32. And we throw away the 1. That's mod 1. And we keep on going. And when I started, I said we take a number like a third. Well, there's a philosophical question. Is 0.33 like a third? It depends on your goals, I guess. So if we start with 1/3, it goes to 2/3, which goes to 4/3, and we throw away the integer, we're back to a third. Once you repeat, you have to keep repeating. And so this, they start close together. If you wanted to start 0.3333, it would take a bit longer, but what happens is this does not behave like this. So we basically have a continuous process here which is diverging fast. Now the difference between these is 1 in 300. And the next one, well, you take two angles and they have a difference. And you double the angle, what happens to the difference? It doubles. Unless you've got a huge angle. So this means this doubles. Do we get 3 in 300? No, because we've doubled these two angles, therefore this doubles. Now that's bad because it's true, but what's happening is it's growing fast. And so it keeps on growing, and by the time we get down to here, it's about as big as it's going to get. I mean, it's more than 1/3 of the circle. So we say this is exponential divergence. And sometimes we talk about how chaotic is something. Well, each time unit, this is doubling. So two solutions or trajectories diverge, doubling the distance between them each cycle. When we talk about weather prediction, there are unknowns in the initial conditions of the weather prediction. And depending on the weather model, but in about 2 or 3 days, the uncertainties in the current state have doubled. And every 2 or 3 days, it doubles again. And so the weather is exhibiting the same kind of doubling. And here the time for the weather would be 2 or 3 days, again, depending on the model you use. Because if you have very fine detail, you will lose the fine detail even faster. So another simple model is something like this, and you can imagine that X represents the density of bugs in your backyard, of some beetles that are going to eat everything in the backyard. And every few days, the beetles increase in number, and until they eat up everything. So when X is small, this is growing rapidly, but when X gets big, they've basically eaten up most of the stuff in the backyard and the population crashes. And so one can ask, can you understand how the behavior of this works? So this is a quadratic, and here I've drawn what they call a tent map, and they have similar behaviors. So this is the theorem, or part of the theorem. Going back, that if you start small, let's say 0.01, and you look at it the next cycle, it'll be something perhaps twice as big, twice as big, twice as big. And so after 3 cycles, it'll be further out to the right. But if you start right here, almost in the middle, and you apply it 3 times, the first one will jump way out here, and here the height is small, and it'll jump way back here, and the third cycle it'll be here. Now this argument I'm giving you, I've never tried in an audience before, but the point is when you start here, after 3 times, you're out here. Got it? Somebody's nodding ahead. Good, good. Okay, now if you start here, and you look at 3 cycles, you wind up in here. Now what happens is I slide this point over. Well, here the third iterate is to the right, and here it's to the left. So somewhere in between, it must come right back to where it is. Got it? So there is some point here, which you could calculate easy with paper and pencil if you pick some slope, such that you iterate it 3 times and it bounces out and comes back where it started. Now, isn't that wonderful? Yes, it's wonderful. You don't know why. Well, because it illustrates the true complexity of this system. We call this a period 3 orbit because after 3 applications of F, you come back to where you started and not before. So, if there is a period 3 orbit, well, there is a period 3 orbit. We've established that, I think. Then, there are infinitely many periodic orbits, just depending on where you start. So there will be some point, pick a number, an integer, 17. There will be some starting point where as you iterate, after 17 times you'll come back exactly where you started. 391, same thing. There will be some starting point, there will be actually a bunch of them, where you start and after 391 iterates, you come back to exactly where you started. Now keep in mind, we're talking about a map like this or a map like this. The argument I gave you works for both. It says that here we have the simplest, basically the simplest model you can imagine. We are not interested in the simplest model except for the fact that it's the simplest model you can write down. And it has this complexity. It has the property that no matter, depending on where you start, you can come back there after any period of time. But if you pick an initial condition, initial starting point, like a third, and you start applying the map, it'll just bounce around, iterate after iterate, just bounce around without coming back to a starting point. Most of the points don't come back to where they start. They just rattle around forever. That's chaos. Again, this is the simplest model you can write down. Or this is. You take your choice. I guess we could say f of x equals 4x. That's simpler. That's a linear model. But for nonlinear models, these are really the simplest. So the point is that what we're seeing here is behavior we can see in the weather models. So there's a scrambled set. Okay, here's what that means. And here's what here's what will actually happen if you pick 2 points at random. Here's 0 to 1. Pick 2 starting points at random. Apply the map to each. You get some new point. Apply it again. Keep applying it. These points, as you watch, will occasionally get close together. But they'll go apart again. And they get closer together and go apart. So I pictured making eggs on a frying pan. You break the egg. Then you start stirring the egg. Miguel, what is Spanish for scrambled eggs? can't quite repeat that. Okay, so scrambled eggs. So we said this is a scrambled, it has a scrambled set. You take 2 points, they come close together. As you're stirring these, 2 egg atoms get close together and go apart, go apart and get closer together. They get arbitrarily close if you wait long enough. I'm assuming that your eggs aren't really being cooked very well. You just keep scrambling them. So the kind of behavior you see in scrambled eggs as time evolution of the scrambling process is what we see in these very simple models. And this scrambled set is, I was in a meeting in Taiwan, and somebody referred to YORKE chaos. And I said, excuse me, what's that? And I got a big laugh because everybody seemed to know what it was, and I didn't. But it referred specifically to this scrambling property of coming closer together. And it's a mixing kind of a property. So we have these 3 kinds of behaviors. And I want to show you, since I've kind of told you that the solar system is pretty quasi-periodic, now let me contradict myself. If you throw in something else like a spacecraft, the behavior can be rather different. And so this is a model in which you think of the sun is always pointing to the left. So imagine you're above the solar system with a camera, and as the Earth goes around the sun, you rotate with it as it goes around. You get the idea, I hope, because I can't do much further than that. So in any case, it looks like this is fixed. And this is the orbit of the moon. And there's a balancing point that's directly between the Earth and the sun called the Lagrange point, where you could put a spacecraft and it would just be stable. It would just sit there, rotating with everything else. However, they don't put it there for technical reasons, namely that if it tries to broadcast what it's seeing back to the Earth, you've got all that radiation from the sun coming back through and it drowns it out. So instead, they find that they've got an oscillation. They can put it in oscillatory orbit. That's going out of the plane of the Earth. So the Earth is going around like so, and this is oscillating around like that. And what happened is, sometimes politics is like football. I'm told that that's what's being played right now in Spain. Politics. And they don't have the same rules that they do in football, so it gets bloody. In any case, somebody said, well, okay, Halley's Comet is coming. We want to send a spacecraft to a comet. And then somebody else said, but we don't have any money for a spacecraft. And the first person says, hey, we want to send a spacecraft to a comet. And the other one says, we don't have any money. So they asked the space scientists what they could do about this and said, hey, we have a spacecraft already out in space, and it's oscillating around here, going around like so, and maybe we can use that. Well, how much fuel does it have on it? Oh, about 100 kilograms of fuel. And where do we want to get this thing to? Well, Halley's Comet got ruled out. But there was another comet coming right past the Earth's orbit, even before Halley's Comet. That was important because the European Space Agency was going to get to Halley's Comet, and we could get there first. Well, nice thinking, but so what they did is they figured out a way of sending this spacecraft with only a tiny bit of fuel on it. So it would move out from the Earth and encounter the spacecraft about 100 million kilometers from the Earth. on a little bit of fuel and in the right place. And I want to show you a little bit about how they arranged this. This orbit was unstable, and one of the things they were using the fuel was that if it drifted off a little bit, they could correct the orbit. Okay, so here we have a 16 kilometer per hour change. This is my bicycle speed, and usually not associated with spacecraft. But by changing the spacecraft speed by 16 kilometers per hour in the right direction, it went in towards the Earth, towards the moon. And now this orbit looks strange because you remember you're looking at this in rotating coordinates. And out it goes. And aha! They timed it just so that it would go in front of the moon. So the moon is coming around like so. So as it's coming, the moon's coming along here, the spacecraft is coming along, and the moon is attracting it. The moon is behind it in this sense. And so it actually slows down. It kills off the momentum. My voice just died. What happened? Anybody have any idea? So here's an intermission for you. So this is called the circular restricted three-body problem. The spacecraft is so small that its orbit does not affect the motions of the planet, the moon and the Earth. And the moon and the Earth are basically going in circles, and everything's moving in the same plane. That's this problem. And there is an invariant, and it's that the kinetic energy plus potential energy minus the angular momentum is conserved if you put it in the right coordinates. Okay, are we on? Good. Now I got 3 things to hold. Okay, intermission is over. We're back. Okay, now here it comes around past the moon on the other side. So you see what happened here is it went in front, the energy got killed off, and it died back down and came back around here. Now it's going behind the moon is attracting it and speeding it up, so it's going to gain energy. This was actually figured out in detail. And you can see how these near passes, depending on exactly how far you go from the moon, it makes a huge difference to this orbit. In fact, you change this a little bit, and when you should be coming back for the 3rd pass, you'll completely miss the moon, or you'll hit it, which is even worse. So Robert Farquhar, a NASA scientist, figured out this orbit in advance, and they implemented it. Here is the 5th near pass of the moon, and it slings it in towards the sun a little bit. And based on this orbit is applied chaos. That just by jiggling things a little bit, just getting it in the right position, they could implement this. Now, you can say, and should be saying, hey, this thing is chaotic. A little change makes a huge difference. This will never work. This is impossible to implement. Nice on computers, but it won't work. Now, that's what the 100 kilograms of fuel was for. What they did is they had to keep correcting the orbit. Okay? They had to keep correcting the orbit. And it went to the comet, went through the tail of the comet, and it was the first successful mission to a comet. And let's give them a good hand here, everybody. So that was the 1980s. That's one aspect of chaos. And there are various aspects of chaos. Now here's a rather different one. we have a pendulum. And we have a clock-like mechanism right here in this pivot here, my shoulder. So we have it so that it keeps it moving. So it's going back and forth. And it can be slowing it down or speeding it up, but in any case, so this pendulum has got different kinds of motions. And one kind of motion it has is a stable motion like this. But by symmetry, there's also one which goes like this. And it's a stable motion. If you start close to this motion, the pendulum will lock into that motion. And there's another one that rocks back and forth. And actually two slight variations of the same thing. But they're basically these three kinds of behaviors. And so we can simulate the starting point. See, when you start up a pendulum, you need the initial angle and you need a speed. So if you tell me the initial angle and the speed, and I have the equations of the pendulum, then I can tell you what's going to happen. And so we have some parameters of the pendulum. And here we have a picture of the result. Now, what we've done here is we've taken 1,000 by 1,000 grid. We've chosen a grid. And for each one, for example, here, that'll be one of our 1 million points. We start the pendulum up with this initial angle and this initial angular velocity. So that's how we start it up. And lo and behold, it winds up locking into, I've got to make a choice. So let's say this one. So we call this the yellow-green solution. So a large number of our initial points started up, wind up, going back and forth. And that's what the yellow points are. And if we start in the red points, it winds up going like this. And the blue ones are the opposite. Okay, so we have these three kinds of behavior. We do 1 million experiments. We color the square, and we get this picture. Now, what's chaos got to do with this? Because I've told you there are these three stable orbits. Well, one of the aspects of chaos is that there can be chaos that's a bit hidden. So if you start the system just right, with an infinite number of decimal places accuracy, it'll behave chaotically. It's on the boundary. The chaos is on the boundary between the yellow region and the blue region. This is another picture. I've taken two pictures, put them side by side, so you can see that the left side and the right side match up. Because this is the initial angle, and the angle 0 or the angle 360 degrees are the same thing, and therefore the pictures should line up. And what I'm going to do, I've got a slightly different picture, but it's the pendulum, and I'm going to zoom in on the boundary. Now, if we were to zoom in on this red region, soon the screen would be full of red. If we were to zoom in on the green, we would see green, and same for blue. So we zoom in, but now instead we zoom in on the boundary. So we start zooming in, and as you zoom in, you keep seeing more and more layers, an infinite number of layers of boundary between boundary between boundary. And we keep on going. You could keep on going forever due to the power of our computers. But I want to point out a particular feature here. We have colored this square, if we can call it that, or maybe we should call it a cylinder. If you take the two sides and wrap it around, you get a cylinder. So we've colored, we've found three regions. These are three connected, the green is connected on this cylinder. And we've gotten three connected regions. Now here's a little mathematical puzzle for you. Suppose you take 3 connected regions in the plane. They don't overlap. But you look at the boundary. How many points can be on the boundary of all 3? Well, you could imagine a disk is one region, and the upper half plane aside from the disk is another, and then the lower half plane. And you've got 2 points. And maybe in plane geometry there'd be some way to prove this, but it would be pretty tricky to prove it. But you can prove things that are false in plane geometry. It's not rigorous. And in fact, it's not true that there are only 2. Because this is an example where there are infinitely many points on the boundary of all 3. So if I took a boundary point, we call this the water property. If you took any boundary point and drew a little circle around it, no matter how small, it would encounter all 3 regions. That's what we mean by it being on the boundary. Okay? So every boundary point has that property, but it's very hard to draw it. However, seeing as how we're looking at something which is so much more complicated than our original model of this quadratic map, now we have a pendulum. And lo and behold, the pendulum is exhibiting this behavior. One of the things you find is that this strange behavior that you couldn't actually, I could give you a week to try to find out how to do this. Without the hint of these pictures, you wouldn't know how to do it. But the computer has more imagination than people do. It'll come up with more scenarios which are meaningful, and sometimes garbage. You have to worry about that too. But they'll come up with, it's a way of testing ideas. Carl Friedrich Gauss in the 1800s knew that by computing he could find out pretty well what's going on. Archimedes, 2,000 years ago, said it's much easier to prove what's going on if you know what's going on. And so he had in mind experiments. And so you want to find out and use the computer to find out what reality is actually like, or what aspects. Every picture that comes out of the computer is a conjecture. You don't know if it's right or not, and you have to explain why that picture is the way it is. So now, zooming in again, you can see that you keep seeing all 3 colors. Now, the dark points are points which take quite a while to eventually enter these 3 basins. And it just keeps on going. The red keeps appearing. The blue keeps, here's some blue coming up. And we call this the water property. There are worse systems than this. But I'm going to take a different approach here. And I'm going to show you a bit more specifically what I have in mind. Is everybody paying attention? Okay. This is my mechanical device called the double pendulum. You see, the red thing is a pendulum, and the silver thing is a pendulum. And there are no motors, no hidden pigeons. If you're going to hide a bird, you should always hide a pigeon, because the pigeons will be quiet. And the parakeets will chop at you. So hide pigeons. But there are no hidden pigeons. And so this exhibits, well, let's see if I can do this. This is a periodic motion, almost, at least. It's pretty close to a periodic motion. And these are the 2 pendulums swinging in the same direction. And here is another periodic motion where the pendulums are swinging in opposite directions. So there's 2 kinds of motions for this, 2 periodic motions for this thing. If you want, this is also a steady state motion. Now, if I start it up like so, this is a quasi-periodic motion. It doesn't look like what you would think. It's not terribly regular, but it's not terribly irregular. I'm ignoring friction here, because if we count friction, everything settles down. So let's assume I've got a perfect picture. I had one once, but I had to throw it out because the thing wouldn't stop. And so you also have chaos. Now what happens here is you think you see a pattern, and then the pattern changes. You see why I woke you up? This is worth seeing. Now, what we're talking about is predictability. And can you predict how it's going to behave? Well, seeing as how there is friction in this one, it'll eventually stop. And in particular, see the red one goes through, goes overhead through the silver one. Eventually that'll stop. It will eventually stop. It will actually stop. Well, I'm not too good at predicting this, but maybe you are. So what we're going to do is play a little game of prediction. And here's what we're going to do. When you think the red one has stopped going through the silver one, you tell me. You get 2 tries. If you're wrong, you get to try it again. And here's how you tell me. Professor York, I want you to know that I think it has possibly stopped. That doesn't work. Okay. Try that. That didn't go very good. That's your way of telling me that you think it has stopped. Okay? Let's practice. Ready? You can clap. You're ready. Ready? Everybody, do it well, please. Ready? Much better. Professor Miguel, would you please assist and watch the audience? It's everybody against everybody else. It's like real society. Stand up and watch. And we want to see who claps first. If you're wrong, remember you got a second try. And I'm getting tangled up in the area. This is dangerous. Yeah, don't watch the, well, you have to watch everything. I don't know what, you've got a tough job, Miguel. Okay. Now sometimes it stops, it's swinging back and forth in a big angle, but the red one is not going through. And so it's a bit hard to predict. I don't know what the formula is for doing this. Looks like I have lost a microphone. Are you paying attention? It's about predictability. You're going to be predicting or not. He's ready. And if you're not aggressive, you won't be first. If you're not aggressive, you won't be first. Now, that's aggressive. You see, it's behaving differently from the first time, right? But we had this aggressive guy here. Were you the one who clapped? He's the one who didn't clap when I asked everybody to clap. Ornery, right? Okay, now, would you stand up for a minute and let everybody see you? Yes, yes. Okay, this guy thinks he knows how to do it. But somebody had to win, right? So let's play a game, everybody against him. Now, who else was close? Who else was very close? There were a couple of people who were almost at the same. Come on, come on. Who feels you were almost on time? You. Okay. the 5 guys behind you are on your team. Anybody else want to join the team, his team? Now, if he actually succeeds twice, he gets to shake hands with Miguel. Are you ready? You're blocking half your team, you know. Okay. Okay. This is a study of chaos in any case. And the world is not predictable. And this chaos is why. Very small changes in your life, as you know, very small changes. You misread one question and you fail the course. And you get kicked out of school. And you lose your job. And the European Union says, don't feed the poor. And you die because you misread the question. Multiple tries. Did you get it? I couldn't tell, right? I think we can declare whoever won the winner. Did you win this? You were pretty close, right? We will declare him the winner. So we have a true genius among us. So, if you want help on that exam, you can read the damn question, he says. There you go, you get the advice. So, I think that's enough for today. You have learned about predictability, and chaos is unpredictability. So, thank you for coming. Now, the message to take home is existan 3 tipos de movimiento: periódico, quasi-periódico, e chaotico. Questions? Miguel made me memorize that. You must have chaos. We've covered all of your lives. How did your parents meet? In Spain, they lived next door. But otherwise, I met a woman I was talking to this week, and she said that her parents were from opposite ends of Spain, and they went to London by chance and met in London. And then they came back to the opposite ends of Spain, and it took a lot of work on the part of these two to be able to continue to collaborate. And now they have 2 kids, and the 2 kids are in college. And where would the kids have been if he missed his flight? That's what life is like. Questions? Yes, in the back. In the back.
Hi. Una cuestión.
Hi.
for us to understand, because if with little difference the outcome is really completely changed, that's maybe because we call it little changes, but I don't know. What is your opinion about that?
Okay. What you said could be completely true. But keep in mind, the system we're talking about includes this particular system. It includes the angle doubles the angle. So, I mean, you are correct that you basically will not be able to predict the motion. There will be regularities of the chaos. For example, these numbers will never leave the interval from 0 to 1. So there's a regularity there in this particular case. So you are correct in saying that, well, we just can't work. But keep in mind that the simplest models have this property. So does that clarify? The reason we pick these models is, for one thing, they're chaotic, but also they're extremely simple. We study the pendulum not because we love pendulums, but because very few systems are as simple as the pendulum. So this means that, well, maybe if we put a lot of friction in the pendulum, it wouldn't behave chaotically. That's true. But every system is going to behave chaotically for some settings of the friction and power and so on. That's not a law, but it's a pretty good rule of thumb. So I agree with you, but that's the world we're living in. And if you only studied Newton, you wouldn't be aware of this overlying universe. And you wouldn't know why your life isn't like the moon, which goes around and around and around and around and around and around. Maybe you do feel like that sometimes, but when you're taking exams. But basically, our lives are sensitive to initial data. Very tiny changes can produce big changes. So thank you for your question. Here's a question. By the way, there's another 2 hours of this lecture. Never mind.
I suppose that there is a point, depending on the interval of time that you are considering on the system, at which the quantum mechanics forbids you.
I think your thing is turned off.
Oh, sorry.
Is it?
I think it's okay.
Okay.
Okay, I mean, to predict the future with a certain accuracy, and the future is longer and longer away, then I guess at some moment it's quantum mechanics prevents you from being able to predict the future.
Right.
Because at some moment you need to know the present with a degree of accuracy that is not compatible with Heisenberg's uncertainty principle. Therefore, after that moment, the lack of the inability to predict would be intrinsic, would be forbidden by quantum mechanics. So could you comment on that?
James Clerk Maxwell, before quantum mechanics, understood chaos.
And he wrote a paper on free will. I think it was a debating club type of paper. And he says, if you knew where every atom was in a leopard. Now, he studied the motion of atoms and them colliding. His gas laws are a fantastic work of art, and how atoms collide. And the first lemma he has in his gas laws, you take two hard sphere atoms. Imagine they're hard spheres, and they're zooming towards each other, and ignore the cases where they miss. But they're coming in with equal and opposite speed, and they collide. What's the most likely direction for them to go in? And what he says, this is the first lemma of gas laws. He says, if you do the calculations, all angles are equally likely. Okay? This is sensitivity to initial data. He understood sensitivity to initial data. And what he said about the leopard is that if you knew the position with any plausible accuracy, you wouldn't be able to predict what the leopard is going to do, because almost instantly you'd have no idea where the atoms would be due to these collisions. So you don't need quantum mechanics at this level. But he said, he understood the regularity of chaos. He says, see, remember leopards have spots. And so he said, the leopard will not change its spots. That's what he says. So he's recognizing that there is regularity in chaos. There are limits to chaos. Now, if we're talking about Mercury, Mercury has a chance of, according to calculations, about 1 in 100 of coming close to Venus in the next billion years. Don't worry about it. Don't worry about it. And it might collide with Venus or whatever. But the point is, quantum mechanics is not going to affect that. But if we're dealing with very small motions, quantum mechanics will affect it. And I think my life is hard enough only worrying about chaos and not quantum mechanics. But yes, quantum mechanics has to be considered for many of these motions. Quantum mechanics is a source of uncertainty. Chaos is a source of uncertainty. Anybody else? The winner, please. I hate it when geniuses ask questions.
I'm wondering if all chaos are equal, or if there is something that, I mean, we can say in some sense that one system is more chaotic than the other system, or, you know what I mean? If there is some way of characterizing the chaos, or...
Well, one way of characterizing chaos is the doubling time in uncertainty. Now you take the leopard.
And you've got these two atoms, and they're moving towards each other, and they collide, and all of a sudden the uncertainty has increased by a factor of maybe 100. Okay? And what is the time scale on the average for two atoms to hit? It's, what, femtoseconds. Definitely. So the doubling time for atoms in the leopard is 10 to the minus 15 seconds, let's say. But for the weather, it's 3 days. So this is one measure. Okay? How fast, and for Mercury, it's something like 20 million years. So that's one measure of uncertainty. Now, I have told you about these basin boundaries. That's one aspect of chaos. And I've told you about these direct chaoses like the one-dimensional maps. These are two aspects of chaos. My lecture actually has 12 aspects of chaos, but life is short. So there are different ways of looking at chaos. See, in particular, the basin boundary one, you won't see chaos. You could have the experiment in front of you and you won't see it unless you look at it the right way. And the right way is to make this grid of pictures, 1,000 by 1,000 grid pictures, and then all of a sudden you see the effects of the chaos. Okay? You're supposed to ask, what are the other 10 aspects of chaos? That's it, folks.